Hello everyone. Today, just to change something, we are solving a Leetcode problem. And for the start, I decided to go with some sorting problem, in particular sort colors problem, which is available under number 75. Let's read the problem. The problem says, given an array with n objects colored red, white or blue, so we have three types of objects. Sort them in place. So that means we are not creating temporary arrays. We should do it in an array that is given to us. So that the object of the same color are adjacent with the colors in the order red, white, blue. And then there is some additional information. Here we will use the integers 0, 1 and 2 to represent the color red, white and blue respectively. So what that means, we need to have all zeros, red, all ones, white, and all blue objects, all twos, in the order that I just mentioned. Note, you're not supposed to use a library sort function. Of course, we are testing our knowledge of algorithms, not the knowledge of being able to call a library. Okay, let's look at some example. Example is as follows: 202, 110. We know all the zeros to the left, all the twos to the right, and ones in the middle. And then there is some follow-up, but what is important from this follow-up is that a straightforward solution is two-pass algorithm, and we should do one pass with a constraint that we should do it in place. So let's look at some explanation. So the explanation is as follows. What I would like to follow is this sequence of steps. Let's talk about strategy, then our steps, the rules that we did use, and then finally we'll move to implementation. Now, why I chose this particular order? Well, I've seen many tutorials and people jump straight to implementation. And then if you don't know this algorithm, you have no idea what's going on. At the same time, I've seen people tell you, okay, here is an algorithm, here is how it works, let's apply it. Again, now you move to implementation only knowing that there is some algorithm. And it's sort of like, this is a set of rules, just follow. But you have no idea why it's going to work and how it works actually. So what I would like to suggest is the following. We will decide how we want to tackle the problem. Then from this, we will see what are the steps that we need to take to solve it, how actually we need to solve it. And then seeing how these steps work, we hopefully can deduce rules, sort of the rule of nature for this problem. And then knowing this rule, so a law of nature that is applied to this problem, how this solution functions, of course then we can move to implementation. Now let me give you an example. Let's start with the following. Let me get black color. So for example, what if we are given an array like this? 0, 1, 2, 2, 1, I know, 0, 1, 2. What do we want to do? So our idea was, and I will draw it here, to keep all the zeros in one place. Then we have all the ones. And then finally, all the way to the right, we keep our twos. Like that. Now, what is the first thing that can come to mind? Well, you see, we are splitting the whole range, the whole sequence in three parts. And those who are familiar with programming know that it's called three partitioning, but it doesn't matter in this case. What is important is just to notice that there are three parts. Now, if there are three parts, we probably would need to keep track of the boundaries. The boundary here between 0 and 1 and the boundary here between 1 and 2. Now, how can we keep track of boundaries? Well, probably we would need some pointers. We would need something to tell us where is the separation here and the separation over there. So what I propose is to, since we have to follow the order given by the following sequence of colors, red, and let me use for white, gray. So this is white. And then finally blue. Since this is the order, let me use the following naming for our pointers. So what I would do, I would keep red pointer, I would keep blue pointer, and I would keep I pointer. And I pointer is the one who will be doing most of the work, because we will be iterating, having several passes, and this I pointer will be doing the magic of solving this problem. Now, the next question is where we put these R and B pointers. We can put them, for example, over here. We can put over here. We can put over here. We can put over here, all the way to the back at the beginning. So there are all the possible combinations. What I propose instead is to think about specific detail of the problem. And specific detail of the problem, which is maybe not really apparent at the beginning, is that we are not putting all the zeros and then ones and then twos. Essentially what we are doing, we are separating all the ones, and such that all the zeros happen to be on the left and all the twos happen to be on the right. So what I suggest is the following. We keep R pointer over here and we keep B pointer over here. What it gives us? Well, with the convention like this, we know that R points to the first one in a sequence of ones, and B points to the last one in the sequence of ones. In this way, we fully describe what is our sequence. First one, ta 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 ta, last one. And having this approach, we know that all the zeros will be on the left and all the twos will be on the right. So this is the approach. Now, as you probably understand, R doesn't come here by chance. It has to iterate from somewhere. Well, since R denotes the first element, probably it will come from the left. And since B denotes, which is blue, denotes the last one, it probably comes from the right. That said, we know that this is where R starts and this is where B starts. Okay, now we know that we also have I pointer doing all the work, where I should start. Well, if I should start at the end, it makes no sense, because if this is a pointer which is doing all the work, it has to make at least one pass. Actually, it has to make exactly one pass, because it's a part of the problem. Solve it in one pass. So from this we deduce that I should start also over here. Next, once we decided on this strategy, how are we going about the steps? So, for example, this is where we keep R, where we keep I, and this is where we keep our B. Now, what are the rules? What should we do? Well, we know that 0 should be on the left. That's why, in this case, what is probably a reasonable thing to do is to exchange the number 0 in this case at I with the number at R. Why? Well, because we want again to pass all the zeros to the left and to make sure that R points to 1. In this case, it just happens that number at I points to number, that's right, this is an array of numbers. So let's just notice that they happen to point to the same element, but they will not once we start iterating. So over here we modify, we do the following swap. We swap num at I with num at R, which essentially means in this particular case that nothing will happen. Now, what should we do after? Well, we know that R should point to 1, should point to next element. We already did the swap, right? Don't forget that R, as we discussed, is going from left to right, so R should move forward, and that's what we should do. We should increment R and remove this one. Now, what should happen with I? Well, I is actually the one who is doing all the work. It just happens that I had to work with R, not with B. So we should increment I also and see how it evolves through the rest of our algorithm. So it becomes over here. Now, what happens in this case? Well, num at I doesn't point to 0, so nothing to exchange with R to go left. Num at I doesn't point to 2 either, to work with B. So what is the most logical thing to do? Well, this is sort of similarly to if we have I over here. If we have I pointing to one of the ones, what we have to do, we just have to move forward one by one, one by one, one by one through all ones. And that's it. R and B pointers, as you can see in our example here, are untouched. R stays at the same place, B stays at the same place, denoting the first one and last one respectively. So the conclusion is I points to 1, moves to next element, and nothing else is modified. Now, situation changed a bit. What happened now, I points to 2, and we know that 2's have to be all the way on the right. So we have to work with the pointer B. So what we do the swap, we swap num at I with num at B. And it just happens that those are 2 2's, so nothing is changed. But let me override it like this to let you know that we have to make a swap. Now, what happens after? Well, from this element, some element, let's say x, could arrive here to I, so we don't know what's going on over here, but all the way on the right, we know that B got 2, and B should go all the way from right to left, denoting here where is a boundary between 1's and 2's. So what we should do is probably decrement B and shrink the region, make it narrower, as in this case, starting from R and B at limiting cases and making the region smaller and smaller. So we decrement B, and B points right now to 1. Now, let me also remove this. Now, what we know is that I points to 2, it just happened, it arrived from B. What do we do in this case? Well, we know 2's should be on the right. So we flip num at I with num at B over here. So what happens is that one goes here, 2 goes to the right, one goes here, 2 goes to the right, and B, since we've got one B gets decremented because we already know that 2 is over there, so we are safe. Alright, now we look what is the next new iteration. Well, we have I pointing to 1, and we already discussed it's a situation when we go through one by one, one by one, one by one. So we just let I progress further. Now I points to 2. Again, the same story. What is the most logical thing to do? Well, we know that B denotes the separating boundary between 1s and 2s, so we do an exchange between 2 and 0, each to each B points. So this becomes 2 and this becomes 0. Okay, what happens next? Well, since we know B got 2, B gets decremented, and this is where now B is. Let's make it a bit cleaner. Okay. Now, I points at 0. What should we do? We should move 0 to the left. How do we do it? Well, remember there is R pointer, and R pointer should denote 0 to 1 boundary. So this is where we exchange elements. We exchange num at I with num at R. And this is how we move 0 to the left and 1 to the right. Because why? Because 1s is what we would like to keep in the middle, somewhere at the center of our array. So this becomes 0, this becomes 1, right? Becomes 1. Now, after this happened, what happens to our pointers? Well, we know R points to 1, so it's no longer previous elements that it was pointing to. So R gets incremented. Our pointer I couldn't point to 2 because it would work with B, couldn't point to 1 because it would be just incremented, so it was pointing to 1, it did the job, and it gets incremented. And we remove previous versions. And now, once I crossed B, the job is done. What we have here is the following. We have, let me denote it. We have red, as you notice, R pointing to the first element, and we have blue, B pointing to the last element of 1s. And we have, with this, we have a perfectly well separated region of 1s at the center, and we have 0s to the left, and we have 2s to the right. And this is where we were. So from these steps that we just followed, just some logical thinking out loud, what we deduced? Well, we deduced the following. We deduce the following rule. So let me write you a rule here. So the following rule is applied. If nums at I equal to 0, then we flip. Actually, let me better type it in. Let's do the following. So the first rule that we discovered, if nums at I equal to 0, flip nums at I and nums at R. Also do R++ and I++. Okay? Now, second rule, and now it's concerned the right-hand side. If nums at I equals to 2, what we would like to do is to flip nums at I, because we are having I pointing to 2, which shouldn't be, because I should work somewhere over here. So nums at I and nums at B. After that, once I at some point over here will get 2 from the B, we don't know what will happen, we will have to sort it out, but we know what already happens to B. We need to decrement B. And now, third rule, what if I points to 1? Well, that's what we discussed over here, we just keep progressing. So if nums at I equal 1, just progress I, that's it. Let's see if like this would work. Alright, so that's the rule. That's the rule that we discovered. Now, how we are going to implement it? Well, let's look over here for a second. What we are given is a vector of integers. So what we'll be doing, we'll be having a for loop or while loop where the job will be done by I pointer, and our I pointer will be going from 0 all the way until it is less or equal to B, because when it becomes equal or higher, we need to stop. And then we will be checking these conditions. Now let's see how we finally implement it. Okay, let's initialize first our pointers. R to 0, because you remember all the way from the left. I to 0, again all the way from the left. And finally B to nums. If we are starting from 0, we would need length -1. So we would get it with size -1. Okay, we initialized our pointers. Now we can have for loop or while loop. Let's have maybe while loop. So in this while loop, what we'll be doing, and while this condition is not met, which means while I is still traversing our sequence and is smaller or equal to B. So while this is the case, we start checking our conditions. So the first condition, if nums at I equal to 0, which means our I hit some 0 and this 0 should be on the left. Well, what we would do, we would swap num set I with nums at r. And don't forget that after that we would need to increment r and I. So what I would use is postfix increment. Okay, so we satisfy this condition. Now else if another condition. Another condition is when nums at I equals to 2. So nums at I equals to 2. What should we do in this case? Well, in this case, as we discussed, we hit a 2 with our I, which should go on the right. So we do an exchange, and we decrement B, which right now is making our R2B region narrower, going from right to left. So what we do is another swap of nums at I with nums at B, and we decrement B. Okay. Finally, our else statement. Well, our else statement in this case is what is left over here is when nums equals to 1 and we keep ones somewhere in the middle at the center. So what we do, we just keep progressing and we increment I. So in this case we would do I++, and that's it. Let's see the logic again. We initialize 3 pointers, r and I at the beginning, b at the end of our vector. We have our while loop, which will be iterating from I equal to 0 at the beginning to b. B initialized being here at the end, at the start, and then b goes right, r and I goes left, sorry, r and I, they go right. Essentially what is happening, this boundary becomes tighter, and the idea is that r points to the first element of ones and b points to the last one in a sequence of ones. And what we did, how we actually accomplished it, is by sequence of swaps, and also don't forget that we need to increment our pointers. Now let's submit. Success, runtime 4 milliseconds, faster than 34% of C++ submissions. So next time maybe we'll discuss a faster algorithm. But what I liked about this one is that we could start with some simple principles, and from these first principles we could, for example here, we could deduce that we need 3 pointers, where they should be located, and they're located over here because we are tightening the boundary. That was our main and first strategy step. Then we, going through example, we deduced what are the steps that should be taken to create this boundary. And from these logical steps, we arrived to rules, how the whole procedure should operate. Once we've done it, the rest was just implementation, took us, I guess, about a minute. And this is how you sort a problem on Leetcode 75 called sort colors. See you next time. Stay humble, stay hungry. Bye bye.